For today's lesson, we want to focus our attention to what we refer to as uniform circular motion. Now, for the past few lessons, we have looked at other types of motion. And if you can remember, we looked at linear motion, and that is when an object is moving in one direction. And that could either be along the x-axis or along the y-axis. We looked at projectile motion, which is now a combination of two types of motion. So when we look at projectile motion, we look at motion happening along the horizontal, and also we look at motion happening along the vertical simultaneously. Now, because we are studying mechanics, right? Mechanics also involves, or not only mechanics, but because we are studying kinematics on a whole, kinematics has to do with describing motion using different types of equations. And one of those motion that we have to talk about is what we refer to as uniform circular motion, right? Now, you might be wondering why is it that we need to talk about these things? But a lot of things that rotate, right? There are certain things that we have to find out in terms of rotation. So take for example, you know, if you wanted to find how long does the Earth take to orbit, you know, the sun and all of that thing, understanding circular motion can allow you to, measure these things and so forth. All right. So in order for us to have uniform circular motion, there are a few things that we have to take into consideration, right? The whatsoever object that is being moved along a circular pattern, it must be at constant speed, all right? So first thing, when we're dealing with uniform circular motion, the speed at which the object is moving has to be constant, meaning that it does not change. So if when the person or whoever it is or the object starts moving from its original position, that speed that it has, that speed will remain constant throughout the entire duration of the object's travel. Now, even though we say that our speed is constant, now for circular motion, the velocity of an object in circular motion is not constant. The reason why we say it is not constant is because the direction is changing. While the speed is constant, the speed, remember, speed is a scalar quantity, and velocity is a vector. So if my direction is changing each time I move around the circular motion, then that tells me that my velocity is going to change, because once the direction is changing, automatically the entire velocity is going to change. All right. So if at this point my object is at this point, right? My velocity, even though my speed will be the same, right? My velocity is going to be a different value because the direction is changing. And whenever you're talking about the direction, or whenever you're talking about the velocity aspect of an object, you have to look at it from a tangential standpoint. And when we talk about tangent, it is just a line that just touches the edge of the circle, right? So imagine that you want to find the velocity at this point, right? Then all you would simply need to do is to just draw a line that is tangential to where the object is located. Good? Now, there are certain things that, in terms of, there are other quantities that will come into play, or yeah, such as what we call the period, right, and the frequency. Now, whenever an object is moving, right, it is moving within a particular time period, right? Now, when we talk about period of a particle that is undergoing uniform circular motion, we can define it as the time taken for one complete revolution. So, if we were to go back to our diagram just now, right? If this is where my object starts from, so if this is my starting point, good? If I were to start my timer at this point, right, where I started, and travel all the way around this this circle, right, back to where my starting point is, I would have completed one row or one revolution. Now, at this very time, I can now get what we call the period. And the period, as we said, is the time taken to complete one revolution. Good? So with that being said, we know something new now. So that whenever we're talking about time, right, in regards to circular motion, that entire time that takes for the object to rotate or to complete one revolution, we refer to that as the time period. Now, another variable or quantity that we will use whenever we are talking about circular motion, that is what we call the frequency. And when you hear about frequency, it is basically saying to you how often something is happening, right? Now, from a rotational standpoint, frequency is the number of rotations made per second, right? Or in other words, we can say it's the number of revolutions per unit time. Now, let's take, for example, if we have a particle that makes n number of rotations in t, right, amount of time, its period is given to us by this equation. So if you got a scenario that said you completed 5 rotations in 20 seconds, in order for you to know how much time did it take to complete one rotation or one revolution, then you would have to divide the time that you got by the number of revolutions. So in my example, my period, which is the time to complete one revolution, would have been equal to 4 seconds. And because we are dealing with time, the unit, of course, has to do with seconds. Now, as it relates to frequency, frequency has to do with the number of rotations per unit time. So in this case, what if I wanted to find out what is the frequency? Now, I would essentially divide the number of revolutions by the time, and this will tell me now how much revolution is happening per unit second, right? And so in this example that I just said a while ago, if n is 5 and the time taken is 20, by way of dividing up these two things, we can find what the frequency is. So the frequency would be 0.25, and the unit for frequency, because we are dividing a variable, a constant by time, then we can see that the units is going to be, you can either say seconds to the minus 1, or you can say per second if you want, or we could refer to it as hertz. Good? So we can refer to the units for frequency as hertz, or we can say per second. All right. Now there are certain relationships when it comes on to period and frequency. We say that they are the reciprocal of each other. So if you know period, right, you can find the frequency because it's the reciprocal of so if you know the period, you can find the frequency, right, by just finding the reciprocal. Good. But how we got this was from the fact that if period is equal to the time taken to complete one revolution, right? And if the scenario was given to us as we had the number of seconds that it took and the number of rotations, we could find out the period. So by this equation that we started off with around here, right? And by way of looking at frequency, frequency would be the number of rotations or revolutions per unit time. So if by taking these two equations, I'm going to take one of the equations and I'm going to make a substitution for one of them. So I'm going to make n becomes the subject for this equation. If I make n becomes the subject in that frequency equation, I now have f times t, right, is equal to n. So if I were to substitute n into my period equation where it says t is equal to the time taken to complete all of those rotations divided by, now because we're substituting for n, we now have f times t. Both t's here will cancel out. So if I cancel out the t's, I have 1 in the numerator, which just show me that I have that my period is the inverse of the frequency. So this is a very useful phenomenon or useful thing that you will use from time to time. If you know the frequency, you can automatically know what the time period is. So by way of transposition, we could make frequency become the subject. So if I were to take this frequency from the denominator and bring it to the numerator, and then by taking the period from this and bring it over here, I will realize that frequency is now equal to 1 upon t. So that's why we say that they are the reciprocal of each other. All right. Now moving along, so we talked about time a while ago. We talked about frequency. Similarly, when you're looking at linear motion, you would have talked about time. You know, what else have we talked about? We talked about velocity a while ago. Well, yeah, but now we're going to talk about angular displacement. All right. Now, just like how in linear motion we have some type of distance, right? When it comes on to circular motion, the distance that we refer to is what we call angular displacement. And you know, from displacement knowledge, we know displacement is, you know, the distance from a starting point to another point. All right. And it's obviously a vector quantity. So in our case here, we use the angle. So whenever you have circular motion and we want to find that distance at which the object is located, all you would simply need to do is to find that angle from the starting point to where the object is now located. Good. Now, whenever we are dealing with angular displacement, it is measured in an um, anti-clockwise way from the x-axis. So let me see if I can draw a quick diagram here to show you what I mean. So if this is my circle, and let me just draw a horizontal line, which is my x-axis. So this is my x-axis. We normally start the angular displacement from the x-axis and move in an anti-clockwise way. So if my object is at this location, right, then from the center to that point where the object is now located, whatsoever angle that is here, that will be my angular displacement, and that will just tell me from how much my particle has been displaced from its original point. Good. Now it is telling us here that the angle theta is defined as the ratio of the arc length swept out by the radius of the circular path. Now, because we're dealing with a circular path, the radius come into play, and you know the radius is half the diameter. So from where from the center to where the object is, right, that is referred to as the radius. From the starting point to where the object is, we call that the arc length, and we refer to that as S. So we now have an equation for our angular displacement. And you can see it right here on the screen that says theta is equal to arc length divided by r. So if I wanted to find my overall angular displacement, all I would just need to do is to find what the arc length, did I say arc length? If I wanted to find my angular displacement, all I need to do is to divide my arc length by my radius, and that will tell me my angular displacement. Good? Now, that is our distance, so to speak, right? Because one of the things that you're going to find out is that the angular displacement, it doesn't have a unit per se, but the unit that we give it based on its angle, we call it radians, right? Because by way of looking at this equation here that says theta is equal to S divided by R. Now S is measured in meters and R is measured in meters because all of those are distances. So clearly we can see that there would not be a unit because those units would cancel out. But for this entire concept of circular motion, we say that our angular displacement has a unit of radians. And at some point we'll talk some more about what radians is, right, on your calculators. Now, if the object that we are rotating, right, completes one revolution, right, by nature of looking at a circle, we know that to complete an entire circle, it is by mapping around the circumference, and the circumference of a circle is equal to 2 pi r. You understand? So my arc length in this case is going to be the entire circumference of the circle. So by replacing that with 2 pi r and dividing that now by the radius, I can realize that my angular displacement is going to equal to 2 pi radians. So whenever you have one complete revolution, that is going to be 2 pi radians. Follow me? Now, whenever we're dealing with circular motion, you will hear us saying that pi is equal to 180. If pi is equal to 180, right, 180 degrees, then 2 pi is going to equal to 360 degrees. And whenever you complete 360 degrees, you have completed the entire circle, right? But don't worry about it now. But just remember that whenever we're talking about 2 pi is just the complete rotation. If you hear we say that the object completed pi, then that is just half of the circle. Now moving along to so we have talked about many things just now. We talked about angular displacement. We talked about frequency. We talked about period. Now, just like when we're dealing with linear motion, there is speed associated with it and all of that and all of those things. When we're dealing with angular velocity, or when we're dealing with circular motion, we will come across a term by the name of angular velocity. And that is just telling us the rate of angular displacement, or in other words, we can say the rate of change of angular displacement. That's what angular velocity is. And you could consider angular velocity as velocity in a sense. But because we're dealing with the circle now, we have to quantify based on the things that we know about the circle. So, by way of looking at the change in angular displacement, so if we treat displacement, angular displacement as distance divided by time will give you a velocity, right? But that's not what we're really doing. We're considering the distance in this case as delta theta, or angular displacement, so to speak. All right. So rather than saying this distance over time, we are now saying angular displacement over time whenever we're dealing with circular motion. Now, but it says now, but since the speed of the particle is constant, it follows that the angle swept per unit time is constant. Hence, the angular velocity is also constant, right? So this is something that you have to pay attention to, right? So because the speed at which the particle is moving is constant, we can then say that the angular velocity is going to be constant as well, all right? Now, we can quantify our angular velocity from another equation. So if we were to consider when the particle has completed one revolution, to complete one revolution, we said that the angular displacement is equal to 2 pi radians, all right? Whenever you complete one revolution, we say that that is now the period. So period is when you complete one entire, is the time taken to complete one entire revolution. So if we were to go back to this equation, since now we're dealing with a complete revolution and angular displacement is equal to 2 pi radians, then we can substitute these things. We can say that angular displacement, or well, angular velocity is equal to 2 pi radians, right, divided by t, capital T for period, right? And we get this equation that says that angular velocity is equal to 2 pi over t, which is the period. Now, because there's a relationship between frequency and period, we can also come up with another equation to say that angular velocity is equal to 2 pi f. So if we were to just substitute for 1 upon t in our equation here, we would get that the angular velocity is equal to 2 pi f. Now, there is a relationship that exists with the linear speed of the particle and the angular velocity. Now, when we're dealing about the linear speed is just the arc length, right, divided by the time. So just like how you would quantify speed would be distance over time. That is the actual linear speed of the particle. But for the angular velocity, we know that the angular velocity is the change in angular displacement with regards to time. Okay, so we want to establish a relationship between linear speed and angular velocity. Now, let's look at a circle, like a literal circle. So I have drawn it here already. So we know that if we have an object rotating from this point, the x-axis, to some distance along the circle here, right? We know that there will be some angular displacement between the x-axis and the radius, and we know that the object will be moving some distance along the arc, which we call that S, and it has a radius R from the center. So we know that our angular displacement is equal to the arc length divided by R, right? Since we know all of this, and we know that, and we know that the linear speed is equal to the arc length divided by the time, we can make a substitution. We can make S, which is the arc length in this equation, becomes the subject. So if we were to do that, you would end up with S equal to angular displacement times R. We're now going to substitute S. So if we go ahead and substitute S, we have V, which is the linear speed, is now equal to angular displacement times R, all of that divided by T. But there is something spectacular happening here. If we were to just group the angular displacement divided by time, we can recall that angular displacement upon time is equal to angular velocity. So, by way of just substituting that, we now have that V is equal to angular displacement times R. So this is that equation that highlights the relationship between linear speed and angular velocity. This is something that we will use eventually. All right. Before we go any further, let's just practice a little bit of what we have gone through so far. Right? So here we have a CD of diameter 12 centimeter, and that is spinning at 200 RPM, which refers to as revolutions per minute. It says for a bit of data located near the edge of the CD, determine the angular velocity. Also, it says determine the linear speed, and it says to us that we need to determine the centripetal acceleration. Now, for part C, we won't be able to do that now, because we haven't talked about centripetal acceleration as yet. But for the others, we can pretty much calculate the other things. So firstly we want to find the angular velocity, and that is omega, right? So omega, by now we can understand several equations that we could, think of, right? We could say angular displacement upon time, but this one we wouldn't use this right now because we don't have all of that information that would require for that. The best possible equation that we can use to find the angular velocity is angular velocity is equal to 2 pi, right? 2 pi times frequency, right? So we could find it. Now, the question gave us several things, right? It gave us the diameter of the wire, of the not the wire, but the diameter of the CD. It gives us the frequency, which is revolutions per unit time, which is in uh, minutes here. So we can say that the frequency is equal to 200, and it says revolutions per minute. But because now we are talking about frequency, frequency really is the number of revolutions per unit time, that is in seconds. So we have to change over that thing about meters, not meters, but minutes to seconds. So in essence, our frequency in this case is going to be 200 divided by 60. When we do that, we get 3.33 hertz, right? So we could use the two different units. We could yeah. So we could have said 3.3 per second, or we could say 3.33 hertz. Now that we found the frequency, we can then find the angular velocity by way of using angular velocity is equal to 2 pi f. So by just working it right here, we have 2 pi times the frequency, which is 3.33 hertz. And by calculation, this would point out rather to be this is going to give us 20.9, and the unit actually is rads per second. At this point, I should have included the rads right here because we know that whenever we complete one revolution, right, we normally say 2 pi rads. So that's what should have been there. So at this point, we should have put rads right here. We know that hertz is per second, so that's how we realize that our answer now must be in rads per second. So it will be 20.9 rads, right, per second. That is the unit for angular velocity, right? Now, they say they want us to find the linear speed. Now, you have to now think back as to what is the linear speed. So the linear speed is equal to v times angular velocity times r, where r is the radius. So this is that equation that links both linear speed and angular velocity. You can only use this whenever you know all of these information. So you need to know obviously the angular velocity, and you also need to know the radius. So in order to solve this, we would put 2.9 radians per second times the radius, which is in meters, right? So because the diameter is 12 centimeters, in order to write that in meters, we will say 12 times 10 to the minus 2, right? Meters. And by way of just calculating this, we should be getting, as a matter of fact, my bad, it's not 12, it's 6, because that's the diameter value, but the half of the diameter is radius, so it's now going to be 6. Yeah. So 6 times 10 to the minus 2 multiplied by the thing here, this value, right? And that should give us some value to say 1.25 meters per second. Okay? So that would be the unit for this particular linear speed. All right, with that being said, we now want to look at what we call centripetal acceleration, right? Now, but before we do that, let's just recap what acceleration really is, because we have to know how to understand it from this standpoint before we can derive it, because deriving it is going to be a little bit of a tedious part. But pre this, acceleration is defined as the rate of change of linear velocity. And as you can see on the screen, right, in order for us to write an equation, we would say that the acceleration is equal to change in velocity divided by change in time. So when an object is rotating around a circular path, we have said it already that the velocity is going to change because there is going to be a change in the direction. Good. So for each step of the way you go from the starting point to wherever you stop, there's going to be some type of vector velocity at that very location. Now, in order for us to do this, right, it's going to require a whole lot of stuff, but I hope that we will be able to can see it and understand this, because what we're about to do is to derive several equations that quantifies the centripetal acceleration. And at some point, I will explain to you what it means by centripetal or centripetal acceleration. Good? Just recall that acceleration is change in velocity divided by time or change in time. All right? Now, let's imagine that we have an object, right, that is moving from point A. So you have an object moving from point A. Now, at the very moment at point A, it will have a velocity VA. Good? Now, when the object reaches at point B, it is now going to have a different velocity because the distance or the location is changing. So our new velocity at this point is going to be VB. Because there's a change in velocity, right, it can tell us that there's going to be some type of acceleration. Now, guys, if you can remember when you're adding vectors, you are to add vectors from a head to tail position. Now, so if we wanted to add these vectors, we would have to ensure that the head of one vector, right, touches the tail of another vector. Follow me? So the best thing to do is in vectors, we can change the direction of a vector, right, just to achieve the head to tail method and put a minus sign in front of it to basically correct the scenario, right? So let me just show you what I mean. So if I have a vector going to the right and I need to change that direction, all I would do is flip it around and put a minus sign beside of it. And that will correct the scenario here. So because I want to put my vectors in the head to tail position, right, all I would now need to do, because this vector right here, vector A, VA, right, it's hard for me to get it in the head to tail position. Because if I were to shift it at this point, it would not be in the head to tail position. I would have to take it And because vector A, so all I would do in this case is to take vector A and turn it around. So instead of having it going like this, I will now have it going in the opposite direction. So this will be what vector A is. But we have to put a minus sign in front of it, similar to what we are seeing at this point. So we still have our vector B going like this. So our vector B is still in that position. But because we're doing vector addition, we now have to add it using the head to tail method. And so we had to take now this vector and put it like this. So when we are trying to now find the change in the velocity, what we would essentially do is to add these vectors, right? So to find the resultant, which is the change in velocity, delta V, we would add these vectors. So we would add VA plus negative V, So we would add VD plus negative VA to find that overall change in the velocity. And so what we would be having here is VB minus VA as the change in velocity. Okay? So we are interested in finding the change in velocity because we want to find the acceleration. And acceleration has to do with change in velocity over time. So I have looked at it here a while ago in terms of, well, not necessarily, right? But this is now from a different standpoint in a sense. So let's look at what this is saying here. So just a while ago, we we came up with this thing to say that our change in velocity is equal to VB minus VA, right? If I were to look at this diagram is the same thing that thing around there a while ago is referring to this diagram, right? So if I were to consider this diagram, the change in velocity would be V2 minus V1, right? So our delta V is going to equal to V2 minus V1. But if we can recall something here, that our angular displacement is equal to the arc length divided by r, and as of such, we can write this thing. We can say that S, which is our arc length, is equal to omega, or in other words, not omega, the angular displacement times r. Since we can recall that whenever we're dealing with speed on a whole, speed is equal to the not the displacement, but speed is equal to the arc length in this case divided by the time. We could substitute for S in this equation. When we substitute for S, we get that V is actually equal to angular displacement times r divided by t. But I want you to see something again, that because we now have r divided by t is also another velocity. It also defines velocity as well. So you can see that because our change in velocity is equal to V2 minus V1, right? And we just found out a while ago that V is equal to the angular displacement times r divided by t. We could substitute those values. We could substitute V2 for angular velocity 2, as you are seeing right here. So not angular velocity, but angular displacement 2 times r, which is the radius, divided by the time. That will tell me what V2 is. Then now for V1, that would be angular displacement times r divided by t. If we were to go ahead and um, do this thing right here, let's do a little bit of manipulation. Since r divided by t is constant, we can factor that out. So we have delta v is equal to r divided by t. In bracket, we have angular displacement 2 minus angular displacement 1. Now, because this is just telling us that we have a change in angular velocity. So in other words, we could write angular displacement 2 minus angular displacement 1 as change in angular displacement. So what we essentially have is angular velocity, well, not angular, my bad. Change in velocity, right, is equal to r divided by t times the change in angular displacement. But just a while ago we said that r divided by t is equal to v. So change in velocity is equal to v times change in angular displacement. Good? What we're doing is just deriving the stuff. So this information here, we're going to use it in something else. So just make note of this to say that change in velocity is equal to velocity times change in angular displacement. Since we can remember that acceleration is equal to change in velocity divided by change in time, follow me, right? We can make a substitution here, and because just a while ago we found that change in velocity is equal to v times change in angular displacement, we can make a substitution for that in this equation. So in essence, we have a, which is the acceleration, is equal to v times delta theta, which is talking about the change in angular displacement, divide now by the change in time. Whenever we talk about change in angular displacement over time or over change in time, we speak about angular velocity. So we can see that our acceleration is equal to velocity times angular velocity. All right, as you can see right here. So it tells us that since omega, which is our angular velocity, is equal to change in angular displacement upon time, we could substitute that by getting that our acceleration is equal to this thing, is equal to the linear speed multiplied by the angular velocity. But there's something that we can also pull back on. Here we have that relationship or that equation that links linear speed with angular velocity. So since v is equal to r times angular velocity, by making omega the subject, we would have v divided by r. So if omega is equal to v divided by r, we can substitute omega, right, in that equation, that acceleration equation. So if we go ahead and substitute that, we would have v times v upon r, which will now tell us that the acceleration is actually equal to v squared upon r. Or we could even say, let's not make a substitution, but let's just let's not let's make a substitution for v, right? So if we were to make a substitution for v, this is what we would have. So we know that A is equal to V times omega. If we substituted for V, we now would have had A is equal to R times omega, which tells us that our centripetal acceleration is also equal to R times omega squared. So there are two equations that we will use whenever we're talking about centripetal acceleration, right? The two main equations are A is equal to V squared upon R, or we can say A is equal to R times omega squared. This is the one that will be most used, right? But in some regards, you can use this to find the angular or the centripetal acceleration. All right? So yes, this just explains what we were talking about here. Now, there's something very important. You might be wondering, why is it that we call this acceleration centripetal acceleration? Now, remember that velocity, it is a vector quantity, right? And whenever we think about acceleration, the direction of an acceleration is determined based on where the velocity is actually directing towards. The change in velocity is pointing towards the center. Here would be the center. So that change in velocity vector is pointing towards the center. So that is the entire reason why we say that this thing is this thing or this acceleration is referred to as centripetal acceleration. It's an acceleration that seeks to go towards the center, right? Or in other words, it always points to the center of the radius. It always wants to point towards the center. So no matter where the object is located, if the object is located here, right, the acceleration, the centripetal acceleration will be pointing that way because the change in velocity would always point towards the center. So it says, based on the change or based on the direction of the change in velocity, right? The acceleration is perpendicular to the velocity. Hence, the acceleration is directed towards the center of the radius along, well, the center of the circle, right, along the radius. And it says now, it is for this reason that the acceleration is called a center-seeking acceleration, which has a value of A is equal to V squared upon R. Now, we'll stop it for today. We'll stop it here, right? In regards to centripetal acceleration or circular motion, there's a lot more things that we need to talk about, right? So that we'll stop here for now, right? So, try as best as possible to can derive these things, right? It's not a must or a guarantee that you have to derive them, but kind of to get an understanding of what is happening, right? You can go through it yourself to see if you understand.